All right, welcome back. So we're looking at Unit 10 here, Unit 10 Final Exam Review. Make certain that you do review your key term language. You can look at the answer keys posted in your classroom for that. So let's get right down to business. If we look at item number 1 here, it's asking for a solution concentration and a percentage. What you need to keep in mind is every solution is made of two parts: solute, meaning what you're making the solution of; solvent, what you're diluting it with, typically water. The total solution amount is always the solute plus solvent amount, and we need to read carefully about whether or not the information provides us the total or it gives us solute and solvent amount. So if we look at number 1, we see there's 150 grams of propanol, which is rubbing alcohol, mixed in 1,250 grams of water. So in this particular concept, what we see if we're calculating percentage, they give us a solute amount and a solvent amount. So our percentage is going to be equal to the amount of solute. So let's make a little fraction bar. Right, solute happens to be water, or excuse me, propanol, 150 grams. Solvent, right, is the water. So they don't give us the total solution amount. They give us the solute and solvent amount. We just need to make certain we're aware that the total is the sum of those two things. And we now have the setup for calculating this. And we would multiply by 100. So we'll take 150 divided by the sum of 150 plus 1250. So that's 1400. 150 divided by 1400. And we'd multiply by 100, and we'd see we get a solution that is 10.7% propanol. Okay. If we look at number 2, again, it's asking for a percentage. So really, we're just going to take the same formula and say, okay, look, we're applying this formula again to get the percentage. So let's apply that same formula. And we'll just do it this way. And here we go. So when we read this one, it says we have 350 milliliters of ethanol. Again, that's our solute, what we're making the solution of. Look at that, a total volume now. So that's how this is different than number 1. They give us the total in this one. So when we go to set this one up, right, now we say percent equals, right, the solute amount, 350, right? And it happens to be in milliliters this time. That doesn't matter. So the total solution amount is 475 now. So now you have a solute compared to a total, and there's no addition in this particular example as a result, right? You would take 350 divided by 475 times 100, and you'll get an answer. So 350 divided by 475 times 100, we get 73.7. And that's percent. In this case, the solution is ethanol. Okay, moving on. We see there's a percentage again. What mass of ethylene glycol would we need to make a solution that has a concentration of this percentage if it's mixed with 750 grams of water? So once again, we have the same formula, but now we're plugging in for an unknown, and we're going to manipulate that formula sort of in an algebraic way to solve. So let's take the formula and we'll take a look at how we're going to manipulate that. So let's set it up. In this case, we know the percentage. So a real quick way to already get rid of that times 100 thing would be to take the percentage they give you and just call it 0.65. So that's sort of like you divided the right side by 100 and the left side by 100 already. So if you call 65% 0.65, you can eliminate the times 100 in the formula. Okay, let's get our solute and solve total amount. So we want to know the mass of ethylene glycol. So we don't know the solute amount, that's X. And what it says, if ethylene glycol is combined with 750 grams of water. So again, we don't know the amount of ethylene glycol, and every solution is solute plus solvent. So that's X plus 750. So if we want a nice, easier way to deal with this, we think of 0.65 as a fraction. We can cross multiply. When we do that, we'll end up with an equation. And we'd take 1 times X, which would be 1X, 0.65 times X, right? We're distributing 0.65 to X and to 750. 0.65 times 750, we get 487.5. So now we have to isolate X. So on each side, we're going to subtract 0.65X. So on the left side, we'll subtract 0.65X, and on the right side, we'll subtract 0.65X. Right, and that's going to leave us with X isolated on one side, right? We're just doing this algebraically. We get 0.35X is equal to 487.5. And then we just divide each side by 0.35 because that's what's attached to X. So 487 divided by 0.35, and we get 1,393. And because this is a mass, right, we get a gram amount of ethylene glycol. I'll just abbreviate it. There we go. And lastly, again, another percentage style problem. What volume of acetone? So we want a volume amount now needed to prepare. Well, again, we got the same version of the formula. So we're going to have solute amount, right, divided by total solution amount, right? So let's just set this up. What volume of acetone? So in this case, we know the percentage again. So let's plug in 0.8. Right, that'll eliminate having to multiply by 100 on the right side. 0.8 is equal, we'll make our little fraction bar. Right, X, we don't know the amount of acetone. We're trying to figure out that volume, but we do know the total now. So now on the bottom, I don't have to add X because it's already been added in there because it says we know the total volume. So we just put 400 on the bottom. And we can think about 0.8 as being a fraction. It's over 1. That will allow us to cross multiply 1 times X, right? That becomes X. And then 0.8 times 400, we would get 320. So the volume would be 320 milliliters. And that's how we go about solving for percentage style calculations. There's, excuse me. So you look at your formula and you apply it accordingly. Just keep in mind, total solution amount is on the bottom, and the words need to be read carefully as to whether or not they gave you the total, or you have to add the solute amount to the amount of water that was added. Okay, question 5 is asking us about some molecules. And there's this concept or idea, it's called like dissolves like. So when molecules are polar, they tend to stick or latch on to other molecules that are polar, and they will dissolve to form a solution with other polar molecules. Likewise, non-polar molecules do the same thing. So we've been using this concept called symmetry. If we look at carbon disulfide, if I cut it in this direction, fold it in half, cut it in this direction, fold it in half, I get 2 lines of symmetry. Multiple lines of symmetry generally means that the molecules of it are non-polar, and that would make a solution with other non-polar molecules. So let's just look at our symmetry for these other molecules. Ammonia, a single line of symmetry. That would make that polar. Acetonitrile, a single line of symmetry, makes that polar. Bromomethane, a single line of symmetry, also makes that polar. Silicon tetrafluoride, 1, 2, you could probably even argue 3, 4 lines of symmetry. So that's very symmetrical. Multiple lines of symmetry means that would be nonpolar, and that would tend to make a solution with carbon disulfide. So if we're looking to describe the answer, we say silicon tetrafluoride, because it's like dissolves like, nonpolar, would mix up with other nonpolar molecules. Okay, number 6 is asking about a molarity concentration. Well, molarity concentration, there is a formula for that. This class is not about memorizing formulas, but we want to be able to use it effectively. So the formula for molarity looks like this. N, which stands for mole amount, is equal to M, capital M, molarity, moles per liter, times volume, right? But the volume has to be in liters. So in this context, they're asking for the molarity amount. So molarity we get by dividing mole amount by volume. Notice in the words, they did not give us a mole amount, but they gave us what relates to a mole amount, a gram amount. So the quickest way to deal with this would be to take our mass and divide by the molar mass of the chemical, factoring in there's 2 sodium, 1 sulfur, 4 oxygen. So let's make this a mole amount by dividing the mass given by the molar mass of this chemical. So I'm going to add 2 sodium, 1 sulfur, and 4 oxygen together. And that gives me a total mass called the molar mass of 142.05. That division is going to give me the mole amount that we're interested in, so we can use that in the formula. And that becomes 2.40 mole. And now we can manipulate the formula, right? Molarity, capital M, is mole amount, N, divided by volume, but the volume has to be in liters. So this volume they've provided is milliliters. We moved a decimal 1, 2, 3 positions left, 0.75. So when we go to set this up, right, what we're going to do is we're going to take formula, molarity is equal to N, which in this case is 2.4, over 0.75. That division is going to give us an answer. So 2.4 divided by 0.75. Our molarity concentration is 3.2 molar, or if you prefer, you could call it mole per liter, because that's what molarity is. So there's your concentration. Number 7, also a molarity style problem. They give you the molarity, they give you a volume. So you got an M and a V. Oh, look at that. They gave you M and V. Hint, 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 calculate N. So how do you get N, or the mole amount? Multiply capital M, molarity, times V. Just make certain V is in liters. So to get the mole amount, let's start this problem by getting or creating the mole amount. 1.75 times 0.250, and that's going to equal N, or the mole amount. 1.75 times 0.25, and we get 0.438 mole, and it's asking for a mass. So there's kind of the inverse of what happened in number 6. In number 6, we were given a mass and we wanted to make a mole amount out of it so we could use the formula. Now we're given a mole and we need to make that a mass amount so we can answer the question. So now we use multiplication. We multiply by the molar mass of lead 2 nitrate. The formula has 1 lead. So I'm adding 1 lead, 2 nitrogen, and 6 oxygen. So I take 0.438 times the molar mass for lead 2 nitrate, 331.22 times 0.438, we get a mass of 145 grams Pb NO3 2 or lead 2 nitrate. And that's how we kind of deal with that particular example. Number 8, again, you have a molarity concentration, you have a mass. In this case, this wants a volume. So to get V, we need N divided by M. So let's just kind of quickly show that. V would be N mole amount, right, divided by M, molarity concentration. We don't have N, so let's make it. They gave us a gram amount. We can always make that a mole amount. We just multiply by the, we divide by the molar mass. So 125 divided by, let's see, we'll take 1 iron and we'll add 2 chlorine to that. And we get 126.75 when we do that. That gives us N, the mole amount. So 125 divided by 126.75, we get 0.986 for N. And then we take N, right? That's mole amount. So let's label it that way so you can see that. So we're going to take that mole amount, divide by the concentration, 1.2, and that will give us what we need. So we're going to plug N in. N is 0.986. Right? We're going to divide by M, which they gave us in the words, 1.2. N divided by M gives us V in liters. So let's do that division. 0.986 divided by 0.12. And we get 8.22. 0.986 divided by 1.2, we get 0.82. Right, and that's a liter amount. Spread that out so you can read it. And there we go. That's dealing with the formula related to molarity. So we might get confused about what we might do with number 9 because it mentions molarity, but here's kind of a way to think about why this is different. This particular example gives us 2 concentrations, right? So here we are making a solution by diluting some stock or some more concentrated solution. So it says what volume of 2 molar. So basically what we're saying is this is a V and this is a C, a concentration. To prepare, right, 100 milliliters, that's a volume that has this concentration, 0.5. So we got a V1, C1, V2, C2. So there was a formula we were dealing with for solutions prepared by dilution. It looks like this. C1, V1 equals C2, V2. We plug in. So C1 is 2. Plug that in. V1 is unknown. We'll leave it as V, so 2V. And then C2 is 0.5, right, times 100. And we're going to have 2V is equal to 0.5 times 100, which is 50. We divide each side by 2. V equals 25. Our volume is 25 milliliters. So C1, V1, C2, V2. The way we recognize these style problems is we'll see either 2 volumes or 2 concentrations as we read. So let's read through the next context. What is the concentration? Oh, ding, 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 unknown concentration. What is the concentration? So that's a C of, right, of pairs it together with this V. Now we read, oh, prepared from 15, that's a volume with this concentration. So our C's and V's are paired up. We got 1s and 2s, right? And we can just put this together and solve for the unknown. So let's do that. So concentration's unknown now. So C times 500 gives us 500 C. And then 15 times 2.5. right? So what we do, 500C equals, we've got to multiply 15 times 2.5. We get 37.5. Okay, let's be careful here, folks. Some people are trying to divide this by 37.5 to solve. Isn't 500 attached to C? You got to divide each side by 500, not 37.5. So 37.5 divided by 500. That's going to give us the answer. We get C equal to 0.075, and that's a molarity, or moles per liter concentration. So these concentration volume dilution problems can also apply to percentages. So let's apply it to a percentage here just by reading once again. So 90%, what volume? Oh, look at that, unknown V of, right, unknown C, known V, to prepare 300 milliliters of a solution with a known concentration of 75. So these two are paired up, these two are paired up. So unknown V times 90, 90 V equals, right, 75 new concentration times 300. 90 V, I'm just going to take 75 times 300 to clean that right side up a little. 22,500 on the right side. Divide each side by 90, right? Because 90 is what's attached to the unknown. 22500 divided by 90. And the volume is 250 milliliters. And that's how we deal with our solutions by dilution. I'm going to shrink this graph up a little bit so we can read it. So we read a solubility curve. Really what we see is that the temperature of most solutes as we heat them up and try to prepare a solution, they become more soluble because the curve rises. Now we do see some things that with dotted lines here where the curve falls. Those are generally not ionic compounds. Those are generally gaseous materials. So they kind of have opposite behavior. So this is first context is asking what's the mass of KNO3 that we could dissolve in 100 grams of water, right? The graph gives us the amount that dissolves in 100, right? On the left side, it describes that. So the 100 grams of water doesn't really have anything to do with the problem. So let's get our drawing tool kind of set up to make a nice thick dot of a color that we can actually see. So here we go. So let's take 15 degrees and see where it crosses KNO3. KNO3 at 15 looks like it's approximately right here. So we put a dot there. Then we read across. Well, that looks like we could dissolve about 25 grams. When it's saturated, that's the maximum amount we could expect it to dissolve. So a saturated solution at 15 degrees would dissolve 25 grams, but that's only if it were KNO3. There's a different solubility for every chemical. So in letter B, it's asking about Ki, and the temperature is 20 degrees. So we want to know how much at 20 degrees of Ki we could dissolve. So let's find Ki, 20 degrees. Let's shrink this in a little bit. 20 degrees, Ki. Let's put a nice dot right there. Dot looks to me like it's about 143-ish. So we'll say that guy somewhere about 143 grams when we have a saturated solution. Anything less than 143 grams, that means there's still room to dissolve more. But in this particular context, it said, what amount could we expect to dissolve if we had a saturated solution? Now look at question C. It asks about how much more could be dissolved. That means we're talking about an unsaturated solution, but we do something really similar. So we read 20 degrees, we look at the chemical as NaNO3. So at 20 degrees, let's find NaNO3 and find what the saturated value is. 20 NaNO3. Oh, look at the saturated value at 20 degrees is about 85. Let's go back to the words now. The words are telling us we dissolved 40 grams. So If we're allowed to dissolve 85, but only 40 grams was dissolved, well, there's room for 45 more grams. So we could expect 45 more grams to be dissolved because we have an unsaturated solution. Okay. Letters D and E are just asking us, is the solution saturated or unsaturated? Well, we use the curve to do that. So sodium chloride at 10 degrees. Let's see what the saturated value would be from the chart. Sodium chloride at 10 degrees. So 10 degrees, where does that cross sodium chloride? Here's sodium chloride. Let's read across till it touches 10. There it is, somewhere about 37. So 37 is what is possible. Oh, they say only 25 was dissolved. That's an unsaturated solution, right? We don't have as much dissolved as possible. So let's look at letter E. 50 degrees and the chemical is NH4Cl. So 50 and NH4Cl, 50 NH4Cl crosses right about here at 50 grams. So 50 grams is the saturated value for NH4Cl. Well, let's take a look. Oh, they say 70 grams is dissolved. So we have more than should be possible. That's that condition called supersaturated. That usually only exists for brief moments in time, often when chemicals are cooling off. So letter F just talks about gases. If you look, they actually even show it with nice dotted lines here are our gases. Look at our gas behavior is different. The solubility of a gas decreases as the chemical heats up. The solubility of a solid increases as the chemical heats up. And that's how we answer that part, right? So gases tend to be less soluble as temperature rises, and the opposite is true for solids. If we're trying to answer number 13, we talked about there being chemicals that when they're dissolved or they're molten, they can conduct electricity, whether or not they are what we call an electrolyte. So where it starts is to know what kind of chemical bond or to know if something's an acid or a base. Okay, so carbon tetrachloride begins with a non-metal element. Non-metal elements are always bonded with covalent bonding. And when a chemical starts with a non-metal element, unless it's an acid, it is generally a non-electrolyte. It will not conduct electricity. If we have a chemical that's an acid, it'll always conduct electricity, just whether or not it's going to do it well or not. Well, what's going to determine that is this guy right here. Is it a strong acid or not? This particular acid that we're looking at in the example is not hydrochloric, hydrobromic, hydroiodic, chloric, perchloric, nitric, or sulfuric. So we would assume that we're talking about a weak acid in that particular example. So weak acids are weak electrolytes. They conduct electricity, just not so well. If we're looking at cobalt 2 sulfate, right, we got an ionic compound. Now we got to consult a chart. The chart that we consult is called Solubility Chart. And here's our solubility chart. So we use it like it's a tool. Let's go back to the example. So cobalt 2 sulfate. So we'll look and see what sulfates do in terms of solubility. So here are our sulfates on the chart. It says all sulfates are soluble unless it's calcium, strontium, barium, silver, or lead. This was cobalt. So this is going to be a soluble chemical. Soluble ionic compounds always make strong electrolytes. Tin 2 hydroxide, well, when we have hydroxide ion, that tends to be what we would call a base. And unless it's a strong base, it's going to be a weak electrolyte. So it doesn't look like tin 2 hydroxide is listed here as a strong base. So we're going to say that's a weak base, right? Weak bases make weak electrolytes. So we'll say weak here. Potassium chlorate. So that starts with a metal called potassium. That's not going to be a non-electrolyte then. That's an ionic compound. Let's look at our solubility then. So what's solubility say about chlorates? Basically, it says all chlorates are soluble. So that's going to make a very good electrolyte. That'll be a strong electrolyte as a result. So we will call potassium chlorate a strong electrolyte. Hydrobromic acid, if we find our chart, right, we're going to see it's on the list, right? Hydrobromic is a strong acid. That'll make this a strong electrolyte. Remember, it's those free ions floating around that allow electricity to jump across, and that makes it a good electrolyte. Sodium hydroxide, once again, oh, that's a base. It has the hydroxide ion. Oh, look at that. It's on the list. Strong. So we use our strong acids and bases chart, and we see that that is a strong electrolyte because we have a strong base. Nickel 2 chloride. So we're looking at a chemical that begins with a metal, ionic compound. We want to check the solubility of it. Chlorides, basically they're all soluble unless it's silver, lead, copper 1, or mercury 2. So this is not any of those. So we're going to make the assumption that this is soluble. And soluble ionic compounds make strong electrolytes. Silver chromate, we're going to find out when we look at chromate. Silver chromate does not dissolve in water well. It is a weak electrolyte. Again, silver is a metal. It's an ionic compound. So we look at solubility. Chromates are down here on the insoluble portion of the chart. And the only exceptions are the group 1A metals, things like sodium, potassium. This is not one of those. So there we have it, right? That's our Unit 10 review about solutions. I hope you found this useful. Till the next time, this is Mr. Brewer.